So today our topic is called Hess's Law. And Hess's Law goes back to talking about the change in enthalpy of a reaction. Do you remember what the variable for enthalpy is? It's an H, good. Enthalpy is delta H, right? And we looked at it briefly already using the equation Q plus P times V, right? It's the total heat in the system plus all the pressure and volume relationship within that system. But Hess's law is going to talk to us about the heat of the enthalpy change that takes place in the total reaction. So when a total reaction takes place, the change in enthalpy is usually the change in enthalpy of the products minus reactants. We looked at that a little bit. But Hess, when he was looking at change in enthalpy of reactions, his conclusion was that the change in enthalpy of a reaction is the same whether the reaction takes place in one step or a multitude of steps, right? Or in multiple steps. So we're going to kind of look at what that means on the next slide here. Maybe. Okay. Is that your next slide or was there one before that? This is it? Okay. So here is our main reaction. In all of the problems that we see with Hess's law, we're going to be given a reaction. That might say, calculate the change in enthalpy of this reaction. And then it's going to walk us through kind of these mini reactions that can help us build this final one. So in this case, here's our main reaction. In this case, they gave you the change in enthalpy, right? Usually we're going to be able to calculate that, but in this one, they gave you the change in enthalpy. And then here are the mini reactions for this single reaction, right? In order for this reaction to take place, we had to develop NO and we had to develop NO2. And this is the enthalpy that is formed or that's released in each of these little reactions. Okay, so for these Hess's law problems, you're going to be getting, here's our main reaction, and then here's the small reaction that had to take place to get to our final. Okay, that kind of makes sense so far? You've got a big reaction that you're focusing on, and then these little reactions. For these little reactions, your delta H values will always be given, right? It'll always tell you this is how much heat was required for this reaction and this for this reaction. You won't always get this one, okay? So it says that this reaction is carried out in two distinct steps. Reaction 2 and reaction 3, and then here's our overall one again. So I want to kind of show you how this 68 kilojoules value is actually calculated. Okay, I want to show you how it's calculated. So let's remember here that our overall goal is to be calculating the change in enthalpy of this reaction. Okay, and when I do these problems, I like to have that big reaction written kind of up above so I can make sure I'm focusing on the right thing. But there's the reaction that we're looking for. I want to go look at my mini reactions and figure out which of these compounds or variables or elements, whatever, which of those are important in my final reaction. And I see N2, I need that in my final reaction. I need O2 in my final reaction. And I need NO2 in my final reaction. Agreed? Right, and I've got another O2 right here, but I'll show you how that comes in just a second. Okay, do you see how that goes together? I have components of my big reaction in my mini reactions. Agreed? Okay. We know that the change in enthalpy, or the delta H value for the total, has to be a sum of the mini reactions. Okay, and in this case, when I add together these two mini reactions, I can cancel to NO because I've got one on the product side and one on the reactant side in my mini reactions. And then I can add up what's left over. N2 plus 2O2 yields 2NO2. And does that look exactly like the reaction I'm supposed to have? Right? And so to find how much delta H is for that reaction, all I do is add these delta H values together. 180 minus 112 gives me 68 kilojoules. So that's where that value comes from. So we're going to look at these mini reactions, and we're going to have to manipulate these mini reactions a little bit to be able to see what things cancel out to leave us with the components of our final reaction. Okay, now this problem was extremely simple, right? All we had to do was cancel out NO on both sides, and we're left with the exact components we need of our reaction. All right, but we're going to look at some that require a little bit more work than that. We can't cancel out two reactants or two products. We can add together two reactants on the same side to get us to where we need. We can cancel things that are on opposite sides of the arrow. Okay? So let's look at now on the next slide. You'll see the rules a little bit now for manipulating our mini reactions. Because this didn't take much manipulation. This was just pretty simple addition. Okay? If a reaction is reversed, the sign of delta H is also reversed. So if I have a mini reaction, let's say that I have a mini reaction that says A plus B yields C and delta H is positive 100 kilojoules. If I need B to be on my product's side in my big reaction, can you envision that? You know what I'm saying? If I need B to be on the product side, I can reverse this reaction and end up with C yields A plus B, in which case delta H would equal negative 100 kilojoules. Right? If I reverse the reaction, I have to reverse the sign of delta H. Because in the first reaction, A plus B yields C, it brought in 100 kilojoules worth of heat. And if I do the opposite reaction, break down C to form A plus B, then I would be releasing 100 kilojoules worth of energy. Okay, so we're going to look at that as we go forth in our problems and say, if I need to reverse the reaction, I also have to reverse the sign of delta H. Okay. Okay, this part, that's not really a rule, but whatever. Okay, if the coefficients in a balanced reaction are multiplied by an integer, the value of delta H is multiplied by the same integer. Okay, so let's see what that would look like here. If I look at the same kind of example, if I have A plus B yields C and I've got delta H equals 100. Let's say in my final reaction, I needed it to be 2A. So I would take the whole formula by 2. 2A plus 2B yields 2C. That would give us delta H equals positive 200. Okay, so however you manipulate the chemical equation, you have to manipulate H by the same. The same goes for our last rule, which I wrote in the last rule here. That's not on your slides. I added that afterwards. The rule is just if you divide by a certain integer, you need to divide H by that as well. Okay, that's the only addition I made to that slide. Okay, if the coefficients are reduced or divided by an integer, the value of H needs to be divided by that integer as well. This says two forms of carbon are graphite and diamond. Using the enthalpies of combustion for graphite, calculate delta H for this reaction. So here is our big reaction. That's what we're looking for. And our goal is to calculate delta H. Excuse me. Thank you. Our goal is to calculate delta H. So I need to look at my mini reactions and say, are things in the right place? Right? I need carbon graphite to be on the reactant side. So in my first one, here's carbon graphite. Is it in the right place?
No. Oh,
yeah, because
yes.
Carbon graphite is a reactant, and so that's where I want it to be. Carbon diamond, I want it to be on the product side, and here it is on the reactant side. So I need to reverse this reaction, right? I need to reverse the reaction. So I'm going to rewrite it. For me, it's easiest to go ahead and rewrite it. If I've got a bunch of things that I'm manipulating, it's easiest for me to rewrite the whole set. But since I'm just manipulating the second one, I don't need to do that right now. So I'm going to go CO2 yields carbon diamond plus O2. I like to make sure my arrows are kind of in line so I can really tell where the products and where the reactants are. And so that means delta H for this reaction now is not negative 396, it's positive 396. And then once I manipulate that equation, I like to go ahead and just cross it out so I know I'm not going to be looking at that reaction to cancel or looking to use that as part of my delta H value. Does that kind of make sense? So once I've manipulated that equation, Now I need to start looking at what I need to cancel out, right? I do not need CO2 in my final reaction. I do not need O2 in my final reaction. I'm left with carbon diamond and carbon graphite, which is exactly what I wanted, right?
Do you make a new thing for that now?
You don't have to rewrite them. You don't have to rewrite them if you don't want to. Nope.
Okay.
I'm just going to be able to look here and say, I needed just carbon graphite. Here it is. I needed carbon diamond. Here it is. Remember, here's our arrows, products and reactants. So you can only cancel O2 because they were on opposite sides of the arrow.
Yeah.
CO2 was on opposite sides of the arrow. So now to calculate delta H, I'm going to take 394 plus 396. I'm going to get a positive 2 kilojoules for my delta H of that reaction from there. So consider delta H for the reaction. Here actually is our main reaction down here at the bottom, which I don't love. I would like to move it to the top, okay, so that I can kind of have some room to write. So I'm going to go ahead and rewrite it at the top of my page, and that way I'll have room to write below there, okay? So I'm going to go ahead and do that now. 2N2 plus 6H2O yields 3O2 plus 4NH3.
So
right?
The grams doesn't matter.
This is gas.
Okay.
Gas.
Gas is this.
You should be careful because sometimes we'll see H2O as a liquid and H2O as a gas. Those are two different things. But as long as we don't see any changes here, you can leave them off.
Okay.
Yep. All right, so let me get rid of this guy down here. And no, I'm aiming for this reaction to calculate the delta H. Okay, so I want to look over my mini reactions and see what are some of the things that I need and where do I need them to be, right? I see NH3 right here, but I need it to be a product, right? Right now it's a reactant, but I need it to be a product. So I'm going to write a little R right here so I know I'm going to have to end up reversing that, right? That's easiest for me. Then over here, I've got an H2 on this side, an O2 on this side, and an H2O as a product. So what am I going to have to do to this one? I'm going to have to flip it or reverse it, right? Because I've got H2O as a product, but I need it to be a reactant. You see what the rationale is behind flipping that? Okay, so now I'm going to go ahead and rewrite it. Sometimes it's helpful to kind of draw a line there so I can see like, okay, I'm making a little change here. 3/2 H2 plus 1/2 N2 yields NH3. And then delta H would be negative 46 here. The second one would be 2H2O yields 2H2 plus O2. And that would give me a positive 484. Okay, when I'm rewriting them, I try to be really careful about putting my arrows in the same spot so that I really have a definitive left and right side of my equation, right? That helps me kind of see this one's on the product side, this one's on the reactant side.
So it doesn't matter. I don't even remember what I was going to ask.
Right, the fractions, you'll have to do a little math with fractions, but they'll work themselves out. I just don't really like to start with those. I kind of like to leave them and see if they can work themselves out first, and then I'll go from there. But I can tell right away that I need to make this a 6, so I need to multiply this whole reaction and the H value times 3. Okay, now let's look to the top reaction and see, is there something that I can do to fix that one as well? What's an easy fix I can make for the top reaction? Let's look at NH3 because it doesn't have a fraction. So NH3, I only have one of them. How many of them do I need? 4. So let's go ahead and just multiply this reaction by 4 and see if that can work itself out. And then make yourself a little note over here to multiply that by 4 as well. And then again, I like to kind of draw a line to give me some separation here. So 4 times 3/2 would be 12/2, which would be 6, right? So 6H2 plus 4 times 1/2 is 2, N2 yields 4NH3. And then negative 46 times 4. Does anybody have that done for me yet? Go ahead and grab your calculator if you don't have that quite yet. Okay, thank you. Negative 184. We didn't reverse it again or anything, so it's a negative. It stays there. And then the bottom one, I'm going to take 6H2O yields 6H2. Wait, is that right? Yeah. Plus 3O2. And then 484 times 3, what's that going to be? 1452. And it's a positive. All right, so now let's start looking at, can we cancel anything here? Okay, the H2s can cancel. Well, first of all, actually, I'll even tell you this. If I start getting things that I need in my reaction, I'll kind of underline them or circle them. I need that, I need that, I need that, and I need that. And so I look at, well, what's left over, and then can it cancel? So 6H2 can cancel, and really that's it, right? So the fractions worked themselves out. Don't let the fractions like freak you out. Remember how to deal with mixed numbers, and that will help with the addition of some things. But that worked itself out exactly as I needed to. So you can rewrite it again just to double check. But since I know I've got everything I need, I'm just going to do that math right now. Negative 184 plus 1452. And I'm going to get a delta H value of what? 1268, positive 1268 kilojoules.
Okay, so I think what my question was.
Okay, so if this was another example for getting this stuff down here, if I had 2 of these same types of moles, I could add them together to be able to cancel something in another mini reaction. Okay. All right, so it did give us the full reaction, and then it gave us 4 mini reactions. So we've got a little bit of extra stuff here. Okay. Oops, sorry. All right, so I want to start looking at what I need. Here's something I need. It's on the right side. H2. Here's H2 right here. That's the only one I see. And then B2H6, I see this one as well. Okay.
So you only have to switch these.
So we're going to for sure have to reverse that one, right? Because I need that to be a product. And then I see another problem with H2. Because right now I've only got 1 mole of H2. Do you see H2 anywhere else? Yeah, we're going to for sure have to multiply this by at least 3 since we need 3 moles of it right there. Right, so I want to do as many steps kind of at the beginning as I can, and then I'll go from there to see what else I need to do. So I'm not sure if I can give myself any more space here or not. No, not really.
So can we just completely dismiss D?
No, we still have to take care of it in its canceling. Okay. So you see how here there's an H2O with a liquid? There's an H2O with a liquid. So it wouldn't cancel H2O with the gas. You got to be careful there.
Okay.
So let's leave it for now, and then we'll see what else. But we do still have to take it into account when we do our adding of that. Okay. I'm going to rewrite my equations up top here because I'm out of room. So here, I get some more room over here.
So we do need to take into account S and like S gas.
If there's a change in them, yeah. I don't love writing it out. I'm probably only going to write it out on the one where it matters, on water.
Okay.
You know? Okay, so A for right now is going to stay the same. 2B plus 3 halves O2. And that's negative 1273. I'm going to reverse the second one.
What is there anything in front of that first? Is it 2B?
This is a 2B.
Okay, at the top.
Right there. Oh yeah, sorry. It's just its first reaction. Okay. So second one, I need to reverse the sign on that. third one I want to go ahead and multiply by 3. 3H2 plus 3 halves O2 yields 3H2O. And so then negative 286 times 3.
Does it necessarily matter what order you go in?
What, with the mini reactions?
No, in terms of how you order your products and reactants, if you have like 2 of each.
No.
Okay.
So this is negative 858 after I multiplied this times 3. And then the last one is H2O liquid yields H2O gas. Okay, so let's start examining here. What we have and what we need. We need 2B, so we have that. We need 3H2, we have that. We need B2H6. So we have everything we need. So I think things should start canceling just from there. So let's start looking at what we can cancel. B2O3, one of those. 3H2O,
Yeah.
that's a gas.
Yeah.
Okay, so here's one of them.
Oh wait. That's a liquid.
Okay, we need to multiply this bottom one by 3. You know what I'm saying? Because I've got 3H2O liquid,
Yeah.
and I need 3H2O. So let's go ahead and do that bottom one by 3, and then 44 times 3. See how it's just a puzzle? You kind of just have to see things as you go. So that would be plus 132. Okay, so now, does that part make sense to everybody? Why we did that?
Yeah.
So now I can cancel my liquid water, and I can cancel my gas water. Okay, so all we've got left is O2. So let's look at this. 3 halves O2 plus 3 halves O2. What does that equal?
3.
It equals 3, right? 1.5 plus 1.5 equals 3. So this O2 plus this O2 would cancel that one. So I think we're good,
So that, okay.
right? Do you see what I'm saying?
Yes.
This one would cancel those. So we're going to cancel all that out. And so now I think we're good. Negative 1273 plus 2035 minus 858 plus 132. I think I get 36 kilojoules.